Guys, so in this last video, I'm going to finish up the notes for week of March 23rd. And this is going to be a little bit brief as far as the first two videos. I was a little bit more in depth and thorough as far as giving you the examples, talking about the concepts revolving around them, and even the calculator use. So now I'm just going to go kind of bust through these questions almost not at the pace that you're expected to do at AP exam, because that's like more practice and whatnot, but it will be at a little bit faster pace. And this video I will try to make as brief as possible, but still include all of the example problems. All right, so let's go to begin. We want to know the average velocity. So immediately I know from this unit 1 over b minus a, and the velocity function is going to go in here. Okay, it is in respect to x. Actually, this is t, so let me change that just real quick. My input variable, as you see right here, is t. So it'd be f prime of t dt, and it's from 0 to 3. Okay, so we're talking about an x1 to an x2, otherwise the a value to the b value. Okay, so from low to high. So let's go ahead and start inputting these values. So my b value is 3, whoops, and then my a value would be 0. All right, so this is my initial setup. My velocity function is going to be f prime of t. Since this is my position function given, my velocity function will come from taking the derivative at 3t squared minus 5, and this is the same as the velocity function because it's the first derivative of my position, okay? So let's go ahead and write that into our 1 over 3 from 0 to 3 of this velocity function, 3t squared minus 5, okay? And we are in respect to t, so that my equation becomes the following, okay? The first piece is going to become 3t squared will become t cubed over 3 multiplied with this constant multiple rule. So you see that kind of cancels out. And then the 5 will become 5t, okay? And we're subtracting that. All the while, it still has this 1/3 way out in front that is multiplying all of whatever this is from 0 to 3 as far as your limits of integration. So I'm looking at t cubed minus 5t is going to be evaluated from 0 to 3. And then at the very end, we'll multiply with that constant multiple rule of 1/3. Okay, so let's go ahead and throw in the 3. So we have 27 minus 15. That's my f of b. Let's go ahead and throw in the 0. 0 minus 0. It, of course, is f of b minus f of a. And last but not least, we're going to constant multiple rule that 1/3. Okay, so that we have 27 minus 15 is going to be what? 512. So 12 minus 0 is still 12. When we multiply with this 1/3, we're going to get 4. So the average velocity, because it's velocity, it's going to be 4. So let's go ahead and give it units per time. Okay, it didn't give us like feet per second or meters or miles per hour. It didn't give us anything like that. So we're just going to say units per time. And if this was an average acceleration, we would have said units per time squared. Let's move on. It says find the average value from 0 to 3 of this following function. Okay, so it's a little bit, let me see the average of this velocity. Oh, okay, so if I'm looking for the average velocity, but this time we are given velocity, well then we're just going to go straight to the setup. 1 over 3 minus 0, again that's a and b, so b minus a, and it's from 0 to 3, and since we are already given the velocity function, we don't have to derive the way we did over here. We derived from the position in order to get the velocity because we remember that's the function that is going to go inside of the integrand, okay? So let's go ahead and just write what we were given because that's our velocity function already. We don't have to do any calculus in order to obtain the velocity function. So we have t cubed minus 5t plus 1. It's all in respect to t, and now we can individually take the antiderivatives. Let me go ahead and make this 1/3. And then we have, let's see, t to the 4th over 4. Then we have t squared over 2 with the constant multiple rule of 5. And then we have a positive t. And this is evaluated from 0 to 3. And like before, at the very end, we have 1/3 is going to be multiplied. Okay, so this, pretend like all of this information would go right here. okay? So let's go ahead and plug in 3. So we have 3 raised to the power of 4, which is 81 fourths. And then we have 3 squared is 9, so we have 45 halves. And then we're going to add 3. All of this, is f of b. That's plugging in the 3. Now, when I go to plug in the 0, everything in this respect will zero out. Now, that won't always happen. Most of the time it will, but it won't always. So make sure that you do kind of look at your terms that you have in your antiderivative, and just to double check that it would zero out, okay? Yes, it is f of b minus f of a, and at the end we will multiply it with a 1/3. And if we're doing this by hand, what I would suggest is try to get everything with a denominator of 4. So we're going to multiply this by 2 over 2, and this one by 4 over 4 with an understood 1 underneath the 3. So that we have all of this has a common denominator now of 4, and I have 81 minus 90 plus 12. That's what's inside with the common denominator of 12. So when we go ahead and multiply this 1/3 here at the end, let's see what we get. 81 minus 90 is a negative 9, plus 12 is a positive 3. So we have over here 1/3 times 3/4, okay? And that, of course, would cancel out so that our answer would be 1/4. So the average velocity is going to be units per time, because that's the default unit of measure when we're dealing with velocity. And since we weren't given any units as far as in our problem, we're not, again, going to put feet per second or anything like that. All right, so find the average value from A to B given the velocity function v of t. Okay, so this one is just like generically asking, what would you do as far as just given the velocity and A and B interval? So we're going to go back to the average value function. Okay, so the average value, we want to know of the velocity. So we know it's 1 over b minus a. And since there aren't any numbers here, we're just going to write what they give us. Okay, we're going to multiply it with a to b. And remember, the velocity, since that's what we're trying to find the average of, the velocity function has to go here as the integrand. Okay, and the velocity function that they gave us, the only thing they gave us was v of t. There's not an actual explicit equation. So we're just going to plug that in as such. Okay. Now, to finish this off, this is a conceptual type of question. Default is, you could say f of t, v of t, and a of t, which is going to be the position function, and then the velocity function, and then ending with the acceleration function. But also kind of common with f of t, in this respect and in these contexts, you usually see the variable s, okay? And this is also signifying the position function, that is. So the antiderivative of v of t is s of t, okay? And we are evaluating that first fundamental theorem wise from a to b. And we're still at the very end going to multiply by this 1 over b minus a piece. Okay, first fundamental theorem, we have f of b, which is s of b, minus f of a, which is s of a. And that's just plugging in those limits of integration where the variable belongs. Remember, this b is going to go in here to create this s of b, and the a as well to create the s of a. And at the end, we will multiply by 1 over b minus a. And this is going to be our answer. So you can finish it off by saying s of b minus s of a is the same as b minus a. And again, this is earlier in the notes from today. This is slope. This is y2 minus y1 over x2 minus x1. You've done this since Algebra 1. Average rate of change, aka the average velocity. That's what we've been doing since Algebra 1. Okay, and now we know with calculus that that is equivalent to, if you wrote it this way with an integral, it would be the average velocity with the velocity function being here. Okay, so just to reiterate that, if I wanted to find the average acceleration, okay, if it asked right here for the acceleration, then the acceleration function would go here, and this would be between two velocities. Okay, understand the one level jump that they exist away from each other and how they're both correlated. All right, let's move on. Our next example problem, we have a total distance traveled interpretation. Okay, it's x minus 2, and it's from 0 to 5. Okay, so if this is total distance traveled, and the reason why I know that it's total distance traveled, aka just distance traveled, well, remember, these are all going to be interpreted as positive, all positive displacements. So each displacement, whether it's positive or negative, when we have calculated them, we're going to take the absolute value before adding them all up together. Okay, so step one in this is to find the zero of the given function. So whatever you're given here, set it equal to 0 and solve for x. So we get 2. And that tells us, instead of saying from 0 to 5, we're going to plug it in from 0 to 2, and then the next from 2 to 5. Since this was my only zero of the function, I'm only going to break this up amongst that dividing number, if you will, that where it partitions it out into two separate integrals. Okay, so now that we've done that, we're going to basically just kind of not avoid, but not really think about. We don't need to include the absolute value anymore. We can just solve this out as x minus 2 with parentheses, or we don't even need those. And then we're going to add this x minus 2 over here, because we're already accounting for each individual piece or interval that could be positive or negative displacement-wise. Okay, so x will become x squared over 2, and then 2 becomes minus 2x. We are evaluating this from 0 to 2. And the same thing over here, x squared over 2 minus 2x, that's the same, but this time we're looking at from 2 to 5. Okay, we will add these, but we first have to take the absolute value of whatever we see in red. Okay, so let's plug in 2 into our function to find f of b. Okay, so we have 2 squared is 4, divided by 2 is 2, and then minus 4, that's f of b. And when we plug in 0, we're just going to zero it out. So it's just like subtracting 0, which we don't need. We can just leave it as 2 minus 4. But we have to remember, we have to take the absolute value. So this isn't going to be a negative 2. It's going to actually equal a positive 2. Let's go over here to our next interval. Okay, so we have 5 plugged in to get 25 halves minus 10. And we're going to subtract whenever we plug in 2, which would be what we got over here, the 2 minus 4. And then we will absolute value whatever that is, and then add it down here. Okay, so let's go ahead and figure this out, scratch work off to the side. So we have 25 halves minus 10. To get a common denominator, since this has a 1 down here, I'm going to multiply by a form of 1, which is 2 over 2. We get 25 minus 20 over 2. So this is just 5 halves. So 5 halves is for this piece right here. And this right here is going to be a negative 2. So we have to be careful with order of operations. 2 minus 4 is negative 2. And since I'm subtracting this negative 2, it's the same as adding 2 like this. Okay, since I'm doing this by hand, I'm going to multiply by a form of 1 so that I get 4. So it's 5 plus 4 all over 2, and I would get 9 halves. So I get 9 halves that I'm going to take the absolute value. Well, it's still going to be 9 halves. It doesn't say negative 9 halves. That's going to become a 9 halves. Okay. So adding this all up together, just common denominators. You could have 2 over 2. Whoops, don't cancel that. Which would become 4 halves plus 9 halves, which is going to equal 13 halves. So my answer for this one is going to be 13 halves is that average, is that total distance traveled. So 13 halves, let's just say units. It could be feet, miles, kilometers, whatever it is. 13 halves units was the total distance traveled in this problem here. All right, so let's move on. Our next one, we're given a velocity function for all positive values of x. And if x or g of 3 is equal to 9, then what is the value of g of 6? So right here, I need to recognize I've been given a velocity function, but then I've also been given a position of some kind and asked to find another position. So this immediately takes me to first fundamental theorem. Okay, so where I have the integral from a to b of a velocity function is the change in positions, f of b minus f of a. This is how we do our basic integrals, okay? So what we were given was this g prime or f prime of x, which is that velocity function here. And the correlation that it has are with these two kind of position functions. Okay, so they're on the position level, if you will. And so this is on the position level, and this one over here in gray was on the velocity level. So this is first fundamental theorem of calculus. Okay, so now we're just going to plug in. We see that an a value here and a b value gives me a low to high interval, otherwise 3 to 6. Remember, these are x values that you're going to have as far as intervals are concerned. Okay, so let's go ahead and plug them in. Our a value is 3, and it goes all the way up to 6. And our velocity function is this root of x cubed plus 2. It is in respect to x because our variable is x. And it's equivalent to all of this over here per first fundamental theorem. We're going to say f, in this case, we're going to use g because that's the position function that correlates with that g prime that was given. So we're going to say g of 6, which is the final position, minus g of 3, which is the initial position. Again, this is the final, and then this right here is the initial, okay? So let's go ahead and calculate what is the value of g of 6. We're looking for that. So just like we did in prior notes, we're going to take this minus g of 3, and we're going to actually move it over here by adding it to both sides. And since this was already a positive in front of this integral, we're just going to add it like this. Okay, this is that rearranging. I think it was on video 1 that we started off with notes. Okay, so all we have to do is solve all of this, and we have our answer of what is the value of g of 6. Okay, again, first fundamental theorem. All right, so let's kind of look back at the pieces that we are given. We know that g of 3 equals 9. So this right here is the same as 9. Okay, now I have to evaluate this integral, and it's going to be 3x squared plus 2. Oops, my bad. X cubed plus 2, and it's going to be in respect to x is equal to the answer that we're looking for, which is g of 6. Okay, for the sake of time, I'm going to go ahead and plug this into my calculator and see what I would get. And in fact, this one is a with calculator problem. Okay, sometimes you will have the calculator because we couldn't use substitution for this because you don't have a 3x squared anywhere outside of this square root piece. Okay, so you would not be able to do this actually by hand. So we're going to have to go to the calculator, and we're going to plug in the entire piece. We're going to say 9 plus, let me go back, the integral from, here we go, the integral from 3 to 6, and it's going to be of the square root, move up there, of x cubed plus 2, and it's going to be in respect to x. And we get 38.373, okay? So since that's my answer, I'm going to go ahead and round it up to 3 decimal places. Now you can round or truncate. Truncate just means you cut it off. So if I'm looking at truncating, the answer would be 38.372 because I just write the first 3 digits of the decimal and I'm done. But if I want to round it, either one's going to be correct because AP allows within one 1/1000th of a point for your answer piece. This would be 38.373. Because I'm a rounding kind of person, I'm going to go ahead and write that out. So let me go to g of 6. My final value of g of 6 is going to be 38.373. And by default, remember, just like we did before the break, we're going to do it always in 3 decimal places. Okay, so let's go ahead and move on to our next example, okay? Our next example is looking at a population that's given a differential equation where t is time in days, all right? So days is t, and the initial population is 3,000. So this initial population is when t is 0, okay? So when we say our initial population, t is 0, we could say p is 3,000 we've created this like initial value of a point 0.03000. Okay, so this point 0.03000, let me write it like this, is like our XY input output initial value. So this is our initial value, or our starting point, if you will. Okay. So find the function that gives the population at any time t. So this is definitely like review of concepts that we did before, dealing with what's it called? Differential equations. And yes, you can solve this by doing this whole entire differential equation where you separate out, putting like 6,000 over 1 plus 0.5 t, and you move this t over by multiplying it both sides, and then you do this separation of variables, so you have the integral of dp, and then you get the population is equal to the following. You can do that for sure, and then plug in your values so that you get what are the variables concerned with. Okay, so for instance, if I plug this in and I were to use it as variables to find part B, I could do a shortcut instead of doing all of that work that's concerned with this particular problem. Okay, but let's look at what A is asking for. It says find a function that gives the population at any time. Okay, so what we've just completed in our previous examples, I'm going to kind of rely on first fundamental theorem as far as this F prime relationship that exists between the change in positions that exist. Okay, and I keep going back to this. I'm going to use this, and then I'm going to move this over to where my final position is here, and the F of A will be added to this left side. And this is what I'm really trying to set up with part A. It says find a function that will give you the population at any time. So it almost feels like y equals mx plus b. Otherwise, f of x is equal to mx plus b. Okay, that's the kind of setup that it's looking at. And because of the variables that we're given, okay, my population is my function. So I'm thinking like p of t. Okay, so this f of x, which came from this f of b, is going to become my position function. Okay, so it will be, instead of f of b, we're going to put p of t. Okay, and it's equal to my p of a, if you will, of where I start. Okay, so we can say p of a plus this integral of what I'm writing over here. Let me go ahead and write this out or move this over. This integral here, and our variable is in fact t, so we're going to keep it as t. So it's p of t is equal to p of a plus the following, starting from a, all the way to b. Okay, so that all of this is really, really correlated with this equation right here, the first fundamental theorem. Okay, we know our a value is where we start, and our b value is where we'll end. So this is the start, this is the end. And if our initial population is 3,000 when t is 0, that means a is 0. Okay, so we could say p of a, or p of 0, would be 3,000. So I can go ahead and replace this p of a, otherwise p of 0, let me go ahead and write that in, with 3,000. Okay, and then we still have from 0 to, let's say, t, because we don't know what that time is, and then we're going to have it equal to the integral of the velocity function, 1 plus 0.5t dt. So that my value as far as p of t is concerned, like if I wanted to know what is the population, let's say, since this is days, on day 15, like let's say this is almost like a model that you can kind of even compare to today's current situation with coronavirus. You could say at 0 time there's 3,000 people infected, and this is the change that will incur let's say after 15 days, you could see how much it would get after 15 days per se. Okay, so it has that kind of fill to it. And I just want to make sure that you understand the initial versus the change and how it equals the final amount, the final position, the final population, whatever context it is that you're looking at. But sure enough, this is the answer for part A. Let's go to part B. It says use your answer for part A to find the population when t is 8. So we're just going to, let me copy this. We're just going to copy all of that. And let's move it down here. And we're just going to say when t is 8, okay? And this is for part B. So let's go ahead and change, let's go ahead and change t to become 8. So that's going to be 8. This is going to be 8. Actually, this is going to be 8 right here, okay? So this is our input value, where down here, so it's a little bit tricky, and I'm glad I caught this. This is going to be 0 to 8, because that's our time. So we're going to say 0 to 8, p of 8. And I do have to go back and change this because 8s don't belong here, okay? Because the integral of a constant, that's not how you replace the t. These actually are another variable because otherwise it can't integrate. And we're going to call these x's. Okay, so this is x, this is x, this is x, this is x. Okay, so that this would be x, so that you can actually integrate this piece, plug in 8, minus the, whenever you plug in 0 into the integral of that, and then you add the 3,000. So now when we plug this into our calculator, it will look like the following. Starting at 3,000, we're going to add the integral. Okay. If you need to rewind that, pause it. I do apologize for not putting that x up front first, but that is important. I'm glad I was able to still make sure to bring attention to it. 6,000 over 1 plus 0.5x, and it is x here. And if this is stored, let's say that we store this, we store this as part A's, let's say P of T. Actually, this is P of 8. This is my answer. My answer is going to be 22,313.255. Okay, so P of 8, or the population after 8 days, is going to be 22. Let me go ahead and write it. Is going to be 22,313.255 bacteria. Let's make sure that we put units in our answer and that we round or truncate to 3 decimal places. All right, so that's how you work out those problems. And again, we didn't ever do separation of variables with this. We could have. We've gotten great practice with that when we were working in groups on those whiteboards in class. You guys did phenomenal jobs as far as showing all the steps and trying to get all those points for the AP exam. But at the same time, there is a shortcut, and it's called first fundamental theorem. You just got to know how do the A, how do the B pieces, as far as the interval setup, how do they correlate with their change in position and whatnot. Okay, so you've gotten plenty of practice with these videos with me. Let's see how many we have left. We have 3, 4. Looks like we have 4 problems left. All right, so let's go ahead and move on to this pizza problem. I'm going to set them up, and for the sake of time, I'm going to let you finish them off. And the key is attached in the calendar with the answers as well, okay? So the pizza with temperature 95 degrees Celsius is put into a room to cool at t is equal to 0. So at starting time, my temperature is 95 degrees Celsius. So you can almost look at this like your initial value or your initial point, okay? Then it says the pizza's temperature is decreasing at a rate, here we go, this rate right here is an f prime of x graph. It's a velocity function, okay? So that's how we're going to interpret it. This is a velocity given function. And the velocity function is all of this right here. Whoops. All of this highlighted in gray. That's my velocity function. And my units, it looks like, are degrees Celsius per minute. Okay, so this rate does say that this could be an acceleration or a velocity graph. But in this case, it's a velocity because we're cognizant of the units. And it didn't say minutes squared, okay? It said the pizza's temperature is decreasing. Okay, so temperature is like f of x. And if it's decreasing at a rate, well, then that's going to be f prime of x. Okay, if it said the pizza's velocity, then that would be f prime. And the decreasing at a rate, this would be the acceleration interpretation. Please make sure that you understand which level you are working with. Okay, but they gave us the position and they gave us the velocity function. Okay, so it says estimate the pizza's temperature when t is 5. So t used to be 0, so I start at 0. I ended at 5 minutes, okay? And I can go ahead and use, again, first fundamental theorem to say, what would the final position be, or what would the final temperature be when it resulted at the end equaling 5? Remember, this is that final position time, if you will, and that's going to be your t of 5. Look, already the rearranged, this is t of 0. Okay, that's the temperature at 0 minutes, which we can already just put in as 95 if we want. So let's go ahead and plug in 95. So we're starting at 95. And this key word, it's so subtle, will make this not an addition, but it's actually a subtraction, okay, because it's decreasing. Okay, and we did that with related rates problems and so on and so forth. When f prime of x was negative, then f of x was decreasing, so on and so forth. When f prime was positive, f of x was increasing. So all we have to do is now put in the velocity function that we were given, the f prime of x, which in this case is going to be our r of t. And you can write it like this if you want as well, or you can just substitute whatever they give you and put 6e to the negative 0.1 t. This right here is going to give you your value that when you plug it in, you get what the key says of 71.392 degrees Celsius. Let's go ahead and move on. A student suggests the hours, or between the hours of 1, all right, so this is different, between the hours of 1 p.m., and 4 p.m. The speed of traffic on a certain freeway exit is modeled by the formula this. Okay, so the speed is modeled by this equation that I just boxed. Okay, so where the speed is measured in kilometers per hour, so if this is the speed model and they're saying it's kilometers per hour, we know it's a velocity interpretation. This is your f prime of x, if you will. This is your velocity function. Because it said speed, yes, we know it's the absolute value, but please don't get this confused with total distance traveled, because that's not what's going on right here. Okay, they gave us the velocity function and just called it speed. But we know that it's a velocity because it was kilometers per hour, not like kilometers per hour squared. Okay, so we want to find out, compute the average speed for the traffic between 1 and 4 p.m. All right, so if I go from 1 to 4 p.m., these are my times that are kind of already given to us. Okay, so 1 to 4 p.m., we're going to say the starting time is A and the ending time is B. So it goes from A to B. Otherwise, it goes from 1 p.m. all the way to 4 p.m. Okay, so if you put this down here, you would say from 1 to 4, and it's 1 over b minus a, because it said the average value. Okay, so that's that equation 1 over b minus a from a to b of whatever it is that you're trying to take the average of. So I'm trying to take the average of speed, so the speed equation is all going to go in here. And yes, you could just write s of t if you wanted to, but it's all of this is basically going to go inside, and then you're going to take it in respect to t. This would be your answer, which comes out to like a 65.5 kilometers per hour. Okay, that's how you do that. Now, I'm going to show you just briefly with the calculator what you could do for the sake of time. But before I do, some people like to say, well, if you started at 1 p.m., couldn't you say that A is 0? and that 3 hours later, b would be 3? Well, you can, and all that's going to do is say 1 over 0, or 3 minus 0, which is b minus a, and it would go from 0 to 3. But something's going to be different here, okay? So we're going to look at that here in just a moment and figure out which one should it be, okay? So we have 2t cubed minus 21t squared plus 60t plus 20, okay? It's still in respect to t, and we're going to see what that equals real quick. First of all, let me plug in this one first just to see this 65.5 is in fact correct. So menu14 to clear storage, menu15 to clear my screen. We have a nice pretty fraction going on of 1 over 4 minus 1, and it's multiplied with the integral from 1 to 4, and it's s of t. Now, I'm going to show you something that you can use instead of rewriting this s of t over and over. So let's say we had 2t cubed, and we have minus 21t squared, and then we're going to do plus 60t, and then we're going to do plus 20. And if I stored this as s of t the way they gave it to me in my problem, now I can just kind of use a little bit of a shortcut. And if I need to do this multiple times, I already have it stored as s of t. So I'll say 1 over 4 minus 1, and it's going to be multiplied with the integral from 1 to 4. And now I can just put s of t, because look, it's bolded because it's already saved from the line above. And then I'll get this answer here. So let me go back, press enter to copy it, and then press control enter to get a nice, pretty decimal. Now, this is the answer that we got back here, 65.5, so that did check out. But if I did the interpretation of saying 1 p.m. was time 0 and 4 p.m. was time 3, which was 3 hours later past 1 o'clock, look at the answer that I would get. Okay, so I would get 3, I'd get 0 here. I'm starting from 0, and then I would go to 3, press control enter. It's a different answer. Okay, so it is a different answer. We're going to talk about that here just real quick. All right, so let's keep going with this because this intends to be a place, and you can see right here, I'm going to show you an example that I actually would have made a mistake because I would have chosen this 1 over 3 minus 0, but I think I would have read this too fast because I was interpreting it as far as the number of hours past 1 p.m. So if it said the number of hours past 1 p.m., then 1 p.m. would have been A is 0. Okay, so if this rate modeled the number of hours, the kilometers per hour, where T is the number of hours past 1 p.m., had it said 1 p.m. here instead of noon, then in fact I would have used 0 and 3. This one would have been correct. But because this says past noon, then 1 p.m. is 1 hour. So that means A would be 1 and then B would be 4 because this is the hours that are past noon. So 1 hour past noon is in fact 1 p.m. 4 hours past noon is in fact 4 p.m. So this one would be the correct answer. Okay, so 65.5 kilometers per hour is the average speed for this one. We just got to be careful that we read those small little pieces of when is it representing it as far as past noon or past 1 p.m. And that will help us define what will these limits of integration be. Will they be 0 to 3 with this 3 minus 0, or would they be 1 to 4 with this 1 over 4 minus 1? Because you see, these are going to be the same, but it all depends upon these limits of integration that will change your answer here. Okay, so again, 65.5 is the correct answer. Please be careful with that and make note of that because that's important information. All right, so let's continue. We have, if excuse me, if f of 3 is equal to 5, we're going to look for f prime is continuous, then the integral that we're given from 3 to 8 is equal to 20, okay? And we want to find the value of 8. So here we go again. What we should identify is we have an f prime of x going on, but then we also have two positions that we're working with. So again, that's going to correlate to my first fundamental theorem that I keep writing over and over again. From a to b, the integral underneath the velocity function, actually the area underneath the curve of the velocity function, same thing, is displacement. Okay, so let's go ahead and set this up. We see 3, we see 8. So let's go ahead and write it out as low to high. And then we just need to plug in the velocity function right here. And then we're going to equal f of b, which in this case is f of 8, minus f of 3, which is our initial value or initial position. Okay, final position minus the initial position. We've been doing this over and over now. Well, the thing is, they didn't give us a function now. They didn't give us like f prime of x is equal to something, nor did they give us like a position function s of x where we would have to take the derivative. They just gave us this right here. So we know that all of this piece right here is equal to 20. So I can say all of this is equal to 20. Okay, so let's go ahead and copy that, save ourselves a little bit of time. And then we're going to go ahead and let's erase this piece right here and just make it 20. Okay, because that's that area underneath the curve right there. And we're looking for f of 8. So we're going to go ahead and move this by adding it to both sides. Okay, and then this just goes away. And now we have f of 8 all by itself. And f of 3 is 5. So 5 plus 25, we get the answer of f of 8 is equal to, 25. Let me go back and fix that real quick. This should be a 0. All right, so that's how we do that problem. Let's go ahead and go to our last problem. Okay, so we are given a position function of 1 plus x squared. It is from a to b. We want to find the average value of f. So we want to find the average value of this function that was given to us. So we're going to go ahead and write that function inside the integrand. We're going to take the integral from -1 to 2. And because it's the average value, we have to remember to do 1 over b minus a. So 2 minus a -1, which is the same as just adding 1. So we'll just put plus 1. So we'll get 1/3, and 1/3 is going to be on the outside. And then we're just going to have to do this by hand. As far as the integral of 1 is x and plus x cubed over 3. And it is from a -1 to 2. So that when you plug it in, you're going to get a final answer of 2. Okay, and I'm just doing that for the sake of time. And then find the c where the average value would be equal to f of c. So let's first find what is f of c. Well, f of c is the same as f of x, but you're just going to plug in the variable c where you have your input variable waiting for that value. So we'll say f of c is equal to 1 plus c squared. And if we're trying to find when it actually is equal to 2, so we're trying to find when is it equal to this average value that we found from part A, we're going to put 2 is equal to 1 plus c squared. Therefore, when we solve it, we subtract 1 from both sides, so that c is going to be a plus or minus 1. Because you initiated this square root, remember when that's an even number, it will always have a positive or negative here. You don't do that if it was like c cubed or c to the 5th, and so on and so forth. So your answer could be c is equal to a positive or a -1, but because of our initial interval that was given, as far as -1 all the way to 2 and everything in between, we're looking at only one of these can be the answer, okay? Because it is in between, so parentheses, not brackets, not brackets. It's not including these, it's in between, okay? So we're going to say that c is equal to 1 is going to be the answer there, okay? That has a little bit of inside kind of intermediate value theorem feeling going on there, but that's the value where the 2 would be the average value of this f of c that was given for us, okay? So that completes our notes, guys. If you do have any questions, please don't hesitate to join in. It is Spirit Week. Look at the post on Google Classroom as far as how to earn 5 more bonus points for your mini assessment that you'll have next week. And we look forward to talking to you during live tutorials or post questions on your Padlet. Talk to you later. Have a great day. Bye.